Hello everyone, welcome to this lecture on counting using recurrence equations. Just to recap, in the last lecture we discussed about the rules of permutations and combinations used for counting. We also discussed about permutations with repetitions and combinations with repetition. And we also discussed about combinatorial proofs. So in this lecture we will introduce a new counting technique which is extensively used in discrete mathematics and computer science, and this is basically counting using recurrence equations. So it turns out that there are plenty of instances or counting problems which get significantly simplified by recurrence equations. And to recap, what exactly is a recurrence equation? So you must have encountered recurrent equations of the form of the following. So we all know that we have this factorial function where we know that factorial of n is n times factorial of n minus 1. Okay, so this is a recursive function in the sense that the value of the factorial function on input n is expressed in terms of the value of the factorial function on smaller inputs. In that sense, it's a recurrence equation, right? Similarly, we are all aware or familiar with this famous Fibonacci function where we know that the nth Fibonacci number is the sum of the n minus 1th and n minus 2th Fibonacci numbers. Okay, so again, this is an example of recurrence equation. So our idea here will be that now we would like to count the number of things by formulating recurrence equations, and later we will discuss how to solve those recurrence equations. Okay, so as I said here that there are many counting problems which get significantly simplified by formulating recurrence equations. So let's see an example here to clarify my point. So imagine I want to find out the number of n-bit strings that do not have an occurrence of two consecutive zeros. That means the substring 00 is not allowed to appear in such a string, and we want to find out how many such strings can be there, right? And we want the general answer, namely we want to find the number of such strings for any n. So the way we are going to count this is as follows. We say that let a of n be a function, or a is the function which on input n gives you the number of n-bit strings which do not have two consecutive zeros. Okay, that's the definition of my a of n function. So if I say a of 1, that will give me the number of bit strings of length 1 that do not have an occurrence of two consecutive zeros. A of 2 will give me the value of number of strings of length 2 that do not have occurrences of two consecutive zeros, and so on. That's a definition of my function a of n. Now we want to find out what exactly will the a of n function will look like, or what will be the output of the function a on input n. And I want to set up a recurrence equation for that. That means I would like to express the value a of n in terms of the output of a function on small sized inputs. So for that, what we are going to see here is the following. If we consider any n-bit string which do not have two consecutive zeros, then there are only two possibilities for the starting bit of such a string, right? The starting bit of such a string could be 1. In that case, the remaining n minus 1 length substring should not have any occurrence of two consecutive zeros. Because if two consecutive zeros occur anywhere in the remaining substring of length n minus 1, then the overall string cannot be a valid string of length n bits and without having any occurrence of two consecutive zeros. That's not going to happen, right? So that's one possibility. The second possibility could be that the string of length n starts with 0. If the string starts with 0, and if we want that the overall string should not have any occurrence of two consecutive zeros, then definitely the second position of that string should be 1. Because if the second position of such a string is also 0, and anyhow the first position is 0, then that's a violation. violation of the property that the string has no occurrence of two consecutive zeros. So definitely the second bit position has to be 1. And now what can I say about the remaining n minus 2 bits in this string? I can definitely say that the remaining n minus 2 bits in the string should not have any occurrence of two consecutive zeros, because if 0, 0 occurs or appears anywhere in the remaining substring of length n minus 2, then the overall string cannot be considered as a valid string of length n, right? And now you can see that these are the only two categories of strings of length n. Either the string can start with 1 or the string can start with 0, right? So now let's try to count the number of strings in both the categories. Okay, if I consider category 1, then the number of strings of this category is a of n minus 1. Why so? Because I am interested to count the number of strings of length n minus 1 which do not have an occurrence of two consecutive zeros. And as per the definition of my a function, the number of such string is nothing but a of n minus 1. You take any string of length n minus 1 which do not have an occurrence of two consecutive zeros, and you put a 1 at the beginning of such a string, that will give you a valid string of length n that do not have an occurrence of two consecutive zeros. So that's why I will have a of n minus 1 number of strings in this category. And how many strings in the second category? My claim is that the number of strings in this category is nothing but a of n minus 2, because as per the definition of my a function, the number of strings of length n minus 2 which do not have an occurrence of two consecutive zeros is a of n minus 2. And you take any string of length n minus 2 bits which do not have an occurrence of two consecutive zeros, and you put 0 and 1 at the beginning of such a string, that will give you a valid string of length n bits which do not have an occurrence of two consecutive zeros. And as I said that these are the only two categories of strings of length n which do not have an occurrence of two consecutive zeros, it turns out that the number of strings of length n will be the output of a function on input n minus 1 and the output of a function on the input n minus 2. However, the argument or the discussion that we had holds only if n is greater than equal to 3. Because if I take n equal to 2, right, then this argument won't hold, because if I take n equal to 2, then if I substitute n equal to 2 here, right, then I get a of 0. And a of 0, as per the definition of my a function, is the number of strings of length 0 which do not have any occurrence of two consecutive zeros, which does not make any sense. So that's why this definition of this recursive function holds for all n greater than equal to 3, right? So now you might be wondering, what about the output of the a function on inputs which are less than 3, right? So we will be giving some initial conditions. So these are called initial conditions here. Okay. Why I'm calling them as initial conditions? Because the recursive functions are not applicable for the case when n is equal to 1, and it is not applicable for the case when n is equal to 2. Because if n is equal to 1, then the number of bit strings of length 1 which do not have an occurrence of two consecutive 0, right, is 2, because both the string 0 as well as the string 1 will be considered as valid string. There is no occurrence of consecutive zeros in this string. There is no occurrence of consecutive zeros in this string. Similarly, if I consider n is equal to 2, right, then the possible strings of length 2 which do not have occurrences of two consecutive zeros are 1, 1, 1, 0, and 0, 1. These are the valid strings. And how many such strings you have? 3. That's why a of 2 will be 3. But for any n greater than equal to 3, I can find out the value of a of that particular n by using this recurrence equation, right? So now we know how to count using recurrence equations. The next thing that we would like to do now is how to solve those recurrence equations. And when I say I want to solve a recurrence equation, I mean finding a closed form formula for that recurrence equation. So what exactly that means? So suppose someone gives me this recurrence equation. The recurrence equation is h of n is twice the value of h function on input n minus 1 plus 1 for all n greater than equal to 2, and the initial condition is that h of 1 is 1. Now, if suppose someone asks me, can you find the value of this h function on the input 100? I can say, well, that's not difficult. As per my relation, h of 100 will be twice h of 99 plus 1, and h of 99 will be twice h of 98 plus 1, and so on. But then this is a time-consuming affair, right? I won't be able to do this or solve this very quickly using pen and pencil, using paper pen, right? So that's a difficult thing. So in fact, h of 100 you still might be able to do, but what if I ask you to compute, say, h of 10,000, right? Then you will be stuck. You can't find out the value of h of 10,000 very quickly. Now, suppose I tell you that h of n is equal to 2 power n minus 1. Suppose I tell you. We will verify whether that is indeed the case or not. Now, if h of n is 2 power n minus 1, then as per this formula, h of 1 will be 2 power 1 minus 1, which is nothing but 1. And it's also easy to verify that 2 power n minus 1 is twice of 2 power n minus 1 minus 1 plus 1. That means I can say that this hn function, right, this h of n function satisfies this recurrence condition. Satisfies in the sense it has all the properties or characteristic that are specified by the recurrence equation. If I substitute n equal to 1 here, I get the same initial condition as given in the recurrence function. And indeed, this 2 power n minus 1 is a function where if I substitute n being n minus 1, then I get this recurrence condition. That means this h of n function will be considered as a solution for this recurrence equation. And why it is called a solution for this recurrence? Because it is a closed form formula. Closed form formula means it is just a function of n. Here, h of n, right? It does not depend on the value of h function on previous inputs. It is a function of the variable n. You just substitute the value of n, you will get the answer. That means now, if I ask you what will be the value of h of 100, then you don't have to follow the complicated process. That means for computing h of 100, you need not have to compute h of 99, you need not have to compute h of 98, you need not have to compute h of 97, and so on. You will just go and substitute n equal to 100 in this function and get the answer. And that's all. That's what we mean by solving a recurrence equation, right? So when I say I want to solve a recurrence equation, by that I mean I am interested to find out a closed form formula for that recurrence equation, namely a function in n which satisfies that recurrence condition. Okay. So now we will discuss about the general methods of solving recurrence equations. It depends upon the type of the recurrence equation, right? It's not the case that the same method of solving the recurrence equation will be applicable for every category of recurrence equation. So first of all, you have to understand here that a recurrence equation basically specify a sequence of values, right? So when I say a recurrence condition or recurrence equation, right? So these terms will be used interchangeably. So recurrence equation, recurrence function, and so on, right? All these are equivalent terms. So whenever I am specifying a recurrence equation, basically I am talking about an infinite sequence of values, and the recurrence equation basically specifies the characteristic of the nth term of that sequence, right? That nth term you might either represent as h of n, where h is a function, or you might omit the parenthesis and n, and you can instead write down n in the subscript. Meaning that I'm talking about the nth term of that sequence. So both these notations are equivalent, right? So for instance, when I say about the Fibonacci sequence, we know that a Fibonacci sequence is defined as follows. The first term is 0, the second term is 1, and then after that onwards, the next term is the summation of the previous two terms, right? So I will start getting this sequence, right? So now if I somehow want to specify the nth term of this sequence, I can use two notations. I can either use the notation f of n to denote the nth term of this infinite sequence. So remember, this Fibonacci sequence is an infinite sequence, or I can use the function f of n. Both means the same thing. If I am using this notation f subscript n, then I mean to say, then I will use this notation that f subscript n is equal to f subscript n minus 1 plus f subscript n minus 2 to denote that the nth term of this sequence is related to the previous two terms of the sequence. Whereas if I am using the function notation for denoting the nth term of this infinite sequence, then I will characterize this property by saying that the value of the f function on input n is same as the value of f function on input n minus 1 plus the value of the f function on input n minus 2. Both these interpretations are equivalent. And that's why for the rest of our discussion on the recurrence equation, I will be interchangeably using the term recurrence function or the nth term of the sequence or and so on. Okay. So whenever we are talking about a recurrence function, right, we are talking about an infinite sequence, and we are interested to specify the property or the characteristic of the nth term of that sequence by saying how exactly it is related to the previous terms of the same sequence. Okay. So suppose somehow someone gives me this sequence, infinite sequence. Now I want to characterize the property of this sequence. That means what exactly is the characteristic of the nth term of this sequence. So it's easy to see that the nth term of this sequence satisfies the following characteristics. The first term of the sequence is 1. And if you take the nth term for any n greater than equal to 2, it is twice the n minus 1th term. That means twice the previous term plus 1. So for instance, if you take 7, where n is equal to now 3, 7 is equal to twice the previous term. Previous term will be the second term plus 1. If you take 15, it is the fourth term. It is twice the previous term plus 1 and so on. So that's what is the interpretation of a recurrence equation. Now solving a recurrence equation means if someone gives me a recurrence equation and does not give me the infinite sequence, solving a recurrence equation basically means finding the sequence which satisfies that recurrence condition, right? So if someone tells me, okay, solve this recurrence equation without telling me the infinite sequence, then my goal will be to find out that infinite sequence. But I won't be finding the whole sequence because it is infinite. Instead, I will just find out the closed form formula for the nth term of that sequence as a function of n. That's what I mean by solving a recurrence equation. It turns out that a recurrence equation may have more than one solution. So for instance, if I take this recurrence equation, namely I'm talking about an infinite sequence where the nth term is the difference of twice the previous term and the previous to previous term. Okay, for all n greater than equal to 2. That means for second term onwards, this sequence has this recurrence condition being satisfied. Now, my goal is to find out a possible infinite sequence whose nth term has this characteristic for every n greater than equal to 2. So I will now show you two possible sequences. So consider this infinite sequence whose nth term is 3 times n. You can easily verify that this infinite sequence satisfies this recurrence condition. You take any term, say 6. It is indeed equal to twice the previous term minus the previous to previous term. So 6 is indeed 2 times 3 minus 0. You take the term 9, it is 2 times 6 minus 3 and so on. So this is one of the infinite sequences which satisfies this recurrence condition. Now you take another infinite sequence, namely the sequence where all the terms are 5, and that's why the nth term of this sequence is represented as an being 5. This is also a sequence where the values in the sequence are completely different from the values in the upper sequence, but the second sequence also satisfies this recurrence condition. You take any term of this sequence, it will be 5. And 5 is indeed twice the previous term, which is also 5, minus previous to previous term, which is also 5. So now, if someone this shows that if someone gives me a recurrence condition, then there can be multiple solutions or multiple sequences satisfying that recurrence condition. Okay. So we will kickstart our discussion with some simple methods of solving recurrence equations. We will discuss advanced methods in our later lectures, right? So we will discuss the simplest method called as the iterative method. What exactly we do in the iterative method? So consider this recurrence equation. I am supposed to find out an infinite sequence whose zeroth term or the starting term is 2, and from next term onwards the term is the previous term plus 3. So I have to find one such sequence satisfying this condition. And when I say I want to find out a sequence, as I said, I won't find the entire sequence, but rather I will find a closed form formula characterizing the nth term of that infinite sequence. So this is how we can do that using the iterative method. So we start with a0, which is the starting term. It is given to be 2. Then we will say that, okay, as per our recurrence condition, the first term of that sequence will be the previous term plus 3. The second term of the sequence will be the first term plus 3. And now we have already obtained the value of a of 1. A of 1 is 2 plus 3, so I am substituting that. And if I substitute overall, then I get the second term is 2 plus twice 2 times 3. And now if I want to find out a of 3, again I will apply the recurrence condition. A of 3 will be the summation of a2 and 3. A2 I have already obtained, so I can substitute here. And now you see that I start getting a pattern here. Pattern in the sense that when I'm talking about a of n, okay, then a of n is nothing but I will be having 2 outside plus n times 3. That's the general pattern that I'm getting here. And that's why if I solve and I keep on solving, then I will get the fact that a of n is 2 plus 3 of n, 2 plus 3 times n. And this is now a closed form formula, right? Why it is a closed form formula? Because here a of n, the value of a of n is just a function of n, right? You substitute n equal to 2, n equal to 3, you get whatever we have derived till now. So this will be the solution of this recurrence equation. I can get the same closed form formula as follows. So here what I did is I started with the initial condition and derived the nth condition. I can do it in the reverse direction as well. I will say that, okay, as per the recurrence condition, a of n is this. Then I apply the recurrence condition again on a of n minus 1. I will say that as per the recurrence condition, a of n minus 1 will be 3 plus the previous term, which is a of n minus 2. And if I take 3 outside, then I get that this is equal to a of n minus 2 plus twice 2 times 3. Now, I will again solve a of n minus 2 by applying the recurrence condition. And I will get the value of a of n in terms of a of n minus 3. And now if I continue like this, I will do that till I obtain the initial condition, which is a of 0. And if I stop at a of 0, then I will get a closed form formula for a of n. So now you can see that it doesn't matter whether I go from a0 to an or whether I go from an to 0. In both the cases, I obtain the same closed form formula. The first method here is called as the forward substitution iterative method. The second process here is called as the backward substitution iterative method. Okay, so this is one of the simplest methods of solving recurrence equations. Now, the the recurrence equation that we considered here can be categorized as a linear homogeneous recurrence equation of degree k with constant coefficient. And why we are interested in this class of recurrence equations is that we will now we will next see a generic method of solving this category of recurrence equations. So what exactly is this category of linear homogeneous recurrence equations of degree k with constant coefficient? So there are multiple terms here. So let's decode each of them one by one. The general form of recurrence equations in this category is the following. Okay, you will have a of n being expressed as a linear function of previous terms. Okay, so that's why the name linear, right? So you can see here that a of n here is a linear function of previous terms. Why it is a linear functions? Because the combiners, namely C1, C2, Ck, are constants here, and a of n depends linearly on previous term, namely it depends only the first power of a of n minus 2, only the first power of n minus a of n minus 2, first power of n minus k, and so on. Okay. Why it is called homogeneous? Because the dependency of a of n is only on the previous terms and nothing else. Okay. We will see what exactly non-homogeneous means very soon. Why it is called degree k? Because C of k is not allowed to be 0 here. If C of k is 0, that means A of n does not depend on A of n minus k. In that case, the degree will not be called k. Your C of 1, C of 2, they can be 0. They are allowed to be 0. Okay. But C of k can't be 0 if the degree is k. That's what the degree means here. It's similar to what we say in the context of polynomials. If I say I have a polynomial in x of degree t, then the coefficient of x power t is not allowed to be non-zero. The coefficient of x power t should be non-zero. Sorry, the coefficient of x power t should be non-zero. The coefficients of other powers of x may be 0. But since the degree is t, the coefficient of x power t cannot be 0. In the same way, when I say degree k, this ck is not allowed to be 0. And the constants coefficients basically says that my combiners are constants here, C1 to Ck. Okay, so let's see some examples of this category of recurrence equations. Your well-known Fibonacci function or Fibonacci recurrence equation falls in this category. Here the degree is 2. Okay, because f of n depends on the previous two terms. Now this equation is not falling in this category. The problem is that a of n does not depend linearly on a of n minus 2. It depends quadratically on a of n minus 2. That's why it is a non-linear function. Whereas this third function or third equation is not falling in this category because we have a non-homogeneous component here, right? Now, the next thing that we want to show here is that I said few slides back that if you are given a recurrence equation, then there might be multiple solutions for that recurrence equation. And we saw an example as well. Now the question is, when exactly is it possible that a given recurrence equation has a unique solution? Well, it is possible provided you are given initial conditions as well. More specifically, imagine you are given a linear homogeneous equation of degree k, that means Ck is not 0. Then my claim is that if you are also given k initial conditions, that means you are given the value of say a of 0, a of 1 and a of k minus 1. If these values are explicitly given to you, which we call as initial conditions, then there always exists a unique solution satisfying the recurrence condition as well as the initial conditions, right? See, the example that we considered, there the initial conditions were not there. You were just given the recurrence equation, and that's why we found two different recurrence equations, two different sequences satisfying the same recurrence condition. But what I am saying here is that apart from the recurrence equation, you are also given the initial conditions. And my claim is that only when you are given those many initial conditions which are same as the degree of your recurrence equation, then you always have a unique solution. And this can be proved very easily using strong induction. So my claim is that there is only a unique solution satisfying the initial conditions as well as the recurrence condition. This is because since you are given the initial conditions, namely the k initial conditions, the first k terms are explicitly given to you. You can't substitute the first k terms arbitrarily. Now, since the first k terms are given to you, I can say that by applying the recurrence condition on the first k terms, I get the next term. The next term can't be an arbitrary term because my recurrence condition explicitly says that what will be the term vk once I have frozen v0, v1, vk minus 1. In the same way, once I have frozen or decided that what are v1, v2, vk minus 1 and vk, that means these are now my next k, these are the k terms which I am considering. By as per the recurrence condition, by applying the linear function or the recurrence function here, that automatically freezes my next term, which is v of k plus 1. And now this process keep on going. You take the next k terms, apply the linear function, the linear homogeneous function here, that will give you the unique value of v of k plus 2 and so on. That means since my initial conditions are fixed and the number of initial conditions that are given to me are same as the degree of your equation, I will be getting a unique sequence satisfying the initial conditions as well as the recurrence condition. If you take the example where I showed you two sequences satisfying the same recurrence condition, that was because you were not given any initial conditions. And that's why I can fill any initial conditions or any initial terms in those sequences, right? So if I consider that example there, that equation was of degree. So let me go back there. If I see if I can go back there. Yes, I can go back, right? So here, what was happening is you were just given the recurrence condition, you were not given the initial term, right? So that's why I was freezing the initial terms here in two different ways. In my first sequence, my initial terms were 0 and 3. And as soon as I freeze the initial sequence or initial terms to be 0 and 3, that automatically fixes my entire sequence. Whereas if I fit the first two initial terms with 5 and 5, and then apply the recurrence equation, that will give me another sequence. So it is due to the absence of the initial conditions that I was getting two different solutions or sequences for the same recurrence condition. But if you are given the if you are given the initial conditions as well, right, and the number of initial conditions, if they are same as uh, the degree, then there will be a unique sequence or solution satisfy your recurrence condition. So that brings me to the end of today's lecture. These are the references used for today's lecture. Just to summarize, in this lecture, we introduced a new counting method called counting by recurrence equations, and we discussed a very simple method of solving linear equations, namely, okay, you can use that method for solving nonlinear equations as well, depending upon the structure of your equations. So that method is called as the iterative method. Okay, and we saw the forward substitution as well as the backward substitution method under uh, the iterative method, and we also discussed about an important category of recurrence equations, namely linear homogeneous recurrence equations of degree k with constant coefficients. Thank you.